Hello everyone, today I'm going to talk about the value of collaboration in convex machine learning with differential privacy. Data analysis method using machine learning can improve quality of service from private datasets. Having large high-quality datasets improves the quality of the trained machine learning models in terms of the accuracy of predictions. This quality improvement can motivate multiple data owners to share and merge their datasets to form a larger training dataset. For example, each data owner could be a private bank or financial institute. In this case, the private datasets can represent information about loan applicants. The input can be salaries, employment status, and credit rating. The output are the historically approved interest rate per annum by the bank. The learning agent is interested in extracting a meaningful relationship between the input and output using machine learning model and the available training datasets. There is an underlying problem that the smaller datasets are owned by multiple entities with restrictions on sharing sensitive data. So, how to preserve privacy in such case? There are three main solutions. First is by using machine learning using secure multi-party computation and encryption. This method is by aiding non-trivial computational and communication performance overhead. The second is machine learning with differential privacy. Machine learning model is either trained on the aggregated dataset and is obfuscated using additive DP noise, or trained on an obfuscated, centrally located data. The third one is a distributed collaborative privacy-preserving machine learning. In the previous studies, privacy-preserving machine learning often merge multiple datasets and construct one dataset. And this large dataset is usually stored in one location. So we develop DP gradient descent algorithm for distributed collaborative privacy-preserving machine learning. And by carefully scale the privacy budget and select appropriate learning rate, we can maintain privacy guarantees over the entire learning horizon. And we can forecast the quality of the trained machine learning model based on local privacy budget. Now I'm going to introduce our machine learning models. Means the data owners could come to an agreement to share private data. The learning agent could train the machine learning model by solving this optimization problem as shown in this equation. This equation has two components. The first part is a regularizer. This part is used to avoid overfitting. And the second part is the fitness of all data owners, which capture the distance between the outcome of the trained machine learning model and the actual output. Then, the minimizer is to find the gradient descent of this equation. However, data owners may not be able to share their private data. So in this case, the learning agent submit gradient queries to data owners. So instead of the whole data sets, the data owners send the DP gradient response to the learner. And the DP noise makes the response to gradient queries stochastic. And also because gradient is calculated locally by each data owner at the same time. So this also helps to reduce learning operation time for the learner. So here is our proposed learning structure for private datasets. The learner first sends queries, gradient queries to data owners. The data owners first calculate the subgradient responses and then adds DP noise before transmits back to the learner. The learner gathers all DP gradient responses from all data owners and trains a machine learning model. So here's a question, like how to solve the effect of DP noise in convergence of the stochastic gradient descent algorithm. And what learning rate should we choose to prove convergence and reduce the impact of DP noise on the fitness cost? So, What we do is we modify the learning model by carefully choosing a decaying learning rate. Noting the learning rate is inversely proportional to the square of the total number of iteration t. Because DP noise is increased proportional to t, so we can ensure the privacy budget is epsilon value over the entire horizon. Also, the step size is inversely proportional to current iteration number k. This is to reduce the impact of DP noise as the iteration getting close to the optimizer. We observe that the performance of this algorithm can only be assessed under the assumptions of differentiability, smoothness, and strong convexity of the finished course. And these assumptions are satisfied for several machine learning models and finished course such as regressions. So we want to avoid these assumptions and to also reduce the effect of the additive noise. So we propose an algorithm for general convex finite function with a slower decaying learning rate. The learning rate here follows is inversely proportional to square root of k. This is to reduce the impact of DP noise. But the decrease is not as sharp as before, so we introduce the average variable. This must be done to compensate for the slower decay of the learning rate. So by introducing this average function, the learner filters the effect of privacy-preserving noise. So, with our proposed algorithm, the learning outcome can be bounded, and the details of the proof can be found in our paper. For strongly convex finite function with a Lipschitz gradient, the relative fineness, which is the fineness of a private model, compared to the fineness of non-private model, is related to the data size and the private budget value epsilon. So, by observing this equation, if epsilon value increase 10-fold, the learning performance improve 100-fold. Also, a bad apple can spoil the bunch. If we take an extreme example, say the value of 1 with epsilon approaches to 0, then it will ruin the fineness performance for all. So, for general convex loss function, the relative fineness is also bounded as shown in this equation. So we can predict the performance of our proposed algorithms with a knowledge of data size and privacy budget. Collaboration with a conservative data owner is only useful if it has enough information to suppress the impact of its DP noise. Now I'm going to show you how we validate our results with real financial datasets. The experiment here shows the outcome of our collaborations between 3 financial institutes. For example, banks. They are training a machine learning model to automate the process of assigning interest rate to loan applications based on the attribute of the borrower and the loan. Each institute has access to a private dataset of historical loan application and approved interest rates. The value of each epsilon for each institute shows their eagerness for collaboration and how open they are to share their private datasets. So first, we show the convergence of our algorithm. The algorithm is stochastic because the data owners provide a differentially private response to the gradient queries, which is obfuscated with Laplace noise. The effect of the privacy budget on the quality of the iteration is at iteration time t. As the epsilon value increases, the data owner become more willing to share their data, and the performance of the trained machine learning model improves. For example, if we see the figure 2 and figure 3, we increase the epsilon value from 1 to 10. The relative fineness of the algorithm improves about 100-fold. So this matches our theoretical results. So after establishing the desired transit behavior of the algorithm, we will show the effect of the size of the dataset and the privacy budget value epsilon on the performance of the trained machine learning model. The experiment data are fitted to the predictions. For strongly convex loss function with Lipschitz gradients, we can see that the slope of the linear lines in the log-log square is -2. So, our learning outcome of the fairness prediction based on the data size and the privacy budgets is tight. Finally, we consider a few scenarios of collaboration for the data owners. We evaluate the performance of the learning algorithm for different scenarios in which the second and the third data owners have small or large data sets and small or large privacy budget. The first scenario, the second and the third data owners have small data sets with a small privacy budget, so they are reluctant to share due to their privacy concerns. This figure shows that there is no point in collaboration with small data owners, even if the size of the first data owner is really large and is eager to share its data. The relative fairness is still really large. So it does not change significantly with a change of epsilon 1, and it still remains large with a relative large data set n1 equal to 10 power of 5. Hence, no matter how large epsilon 1 gets, the error still remains large due to the small privacy budget of the other two data owners. So the dataset for the first data owner N1 must become really large to compensate for it. When the second and the third data owners have larger datasets, as shown in this figure, the red figure, the relative fairness is better as conservative data owners are relatively large. In the third scenario, the effect of the epsilon 1 and n1 are more pronounced. This is because both of the other two data owners have small data sets. So even they have conservatively small data budgets and there is large amount of noise because of their small data sets, they do not hinder the learning process. So the best scenario for collaboration is the last one scenario. The other two data owners have large data sets with a large privacy budget. The good performance can be achieved even without much consideration towards the size of the first dataset or its privacy budget, and the other two datasets are large and eager to collaborate for learning. So, collaboration can only be useful if the dataset has enough information to suppress the DP noise. We also use a credit card dataset with a linear support vector machine (LSVM) classifier for fraud detection to further show the value of collaboration. We validate our proposed algorithms and the theoretical result for this LSVM classifier, and this can be found in our paper. In conclusion, we have developed DP gradient descent algorithm for training machine learning models on distributed private datasets, and we predict the outcome of a potential collaboration among privacy-aware data owners. And we validate our prediction by evaluating differentially private machine learning models algorithm on the financial datasets. In the future, we can extend the framework to multiple learners aiming to train separate privacy-aware machine learning models with a similar structure based on their own datasets and the DP response from other private data owners. The utility privacy trade-off in this paper, in terms of the quality of the trained machine learning model, the loss function can be used together with the cost of shared private data of the consumer with the learner to set up a game theoretical framework for modeling the interactions across data market. Synchronous updates of this algorithm is indeed a bottleneck of our proposed algorithm. So the future work has focused on extending the result of this paper to asynchronous gradient updates, where at each iteration only some of the data owners update their machine learning model. Another direction for the future research is to extend the framework of this paper to adversarial learning scenarios that can admit more general adversaries than current case of curious but honest adversaries in this paper. Thank you for your attention.